Mode. If you didn't have a chance to draw it, this is what it should look like. It's not perfectly what it should be in the in the handout. In the handout you have more something like 0.9, but it has to do with the fact that this table is not super stable, so it's vibrating at the same time as the rest of the thing and changing the frequency. But it doesn't matter. It's just for you to get an idea of what the first mode looks like. Now I'm going to go to the second one, which is...
So in this, all the floors are moving to the same direction.
Yeah.
And as we go up, the amplitude, the displacements will increase. So typical first.
That one moves a lot more than this one first. Is it 2.9 the second? 3.9. No, 2.9. I'm trying to get the frequency as exact as possible. Well, I guess that's as close as I can get. It's 2.97 in this particular setup. And you can, some things that you can notice, that this floor is vibrating in the opposite direction to this one. So before we had everything going in the same direction, now we have these two going in one direction while this is going in the other direction.
The third one is standing still.
You can, yeah, this is theoretically it should be standing still, but of course, you know, this is a lab experiment, so theory doesn't apply 100%. Another thing you can notice is that while this bend a lot, and so that these are almost straight. So it means that these two floors are vibrating together. They don't move relative to each other, they move relative to everything else. So this is the second eigen mode, more or less. And I'm trying to find the third one, which should be at 4.5-ish. It's a bit too violent. So this will be the third eigen mode. Again, we have something similar to each other. These two vibrate together, so nothing is happening in this beam, while the others shake a lot, particularly this one. So
top one is going on the other direction compared to the first one? Is it?
I think they're going to the same, but I'm not sure. It's hard to see. But they should. Okay. All right. So this is more 4.6 hertz. And you can see the importance of the resonance if I turn down the frequency from 4.6 to 4.4. So the vibration reduces a lot. It's the same force applied, it's still shaking it, but just going up a little bit off the critical frequency reduces the resonance. And if I go beyond, so instead of 4.6, if I go to, for example, 4.8, that's 4.83. Again, it is shaking. You can see it is shaking, but it's a lot less than at the critical frequency. And that's something we all have experienced. Like, and the last one at 5.8 hertz, more or less. Yeah, there you have it. This is at 5.7 hertz, and yeah, you can see that all the floors are vibrating, and they are vibrating each one to it. So it's something that is very typical from the highest mode. It's always the case that each degree of freedom is vibrating opposite to the previous. So it's left, right, left, right, left, right, left, right. That's always the case on the highest vibration mode. And that's what we can see here. Each floor is vibrating, and each one is going to its own side. Of course, the vibration is larger here than here, but they're all still moving. Alright, so now we have a very rough, we can say, kind of hand-calculated or hand-drawn idea of what the modes look like. What you're going to do for the lab is to extract or to estimate the modes again, but from the measured data, so from the plots, which will give you a lot more exact idea of what the modes look like, and from a numerical experiment also. You'll have to simulate the 4 degrees of freedom system and find the eigenfrequencies and eigenvectors, and so you obtain the modes in these 3 ways, like pretty much by eyesight, by the measured data on the plots, and by numerical simulations. All right, so are there any questions? No? Then that's it. Good luck with the lab.